We've described the regions of spaces where electrons can reside in an atom, that is, the orbitals. And what we're going to do now is apply the orbitals to the atom in an overall viewpoint where we can see where each electron lies surrounding the atom. Now, while we don't know the exact space or velocity, we do have a good idea of where it is. And so what we're going to do is we're going to shift to talking about the energy an electron has when they are in these orbitals. The lowest energy orbital, that is the electron that is closest to the nucleus, is in the first subshell. And if you look at the diagram here, you see that the first subshell, or n equals 1, or the 1s orbital, has the energy that is lowest compared to the other orbitals. In fact, 0 is at the top of this plot, so things become more negatively charged or cost more energy the closer they get to the nucleus. This is an example of hydrogen, and hydrogen is unique compared to all the other elements because the orbitals of any given principal quantum number are equal in energy. We describe this as being degenerate when two orbitals have the same energy associated with them. This is why Rydberg's equation works so well, and it's due in part to the simple nature of a positive and negative charge interacting. There are no other factors that we need to consider. However, when we move to other atoms, this degeneracy we see in the orbitals goes away. And so the electron configurations begin to split apart, and we find that there are certain orbitals that always get filled before others. So if we're thinking about a hydrogen atom, then we can see our first electron, or the only electron in the hydrogen atom, goes in the lowest energy state. That is, it goes all the way to the bottom to the 1s orbital, and we put one electron in there. And when electrons surround atoms, they always fill up the lowest energy orbitals first. And electrons will continue to occupy these orbitals in such a way that the lowest energy ones will always be filled before higher energy ones. So think about it as filling a cup up. The cup doesn't start filling up halfway up, it goes all the way to the bottom of the glass and works its way up. The same thing is true with electrons. This idea that electrons fill the lowest energy orbitals first is known as the Aufbau filling principle. Electrons will always move towards the lowest energetic state that's available to them. You can see here in helium, since helium has 2 electrons, both electrons go into the 1s orbital. Now, we've filled the 1s orbital. The 1s orbital is completely full. We can't put any more electrons into it. So if we have to put a third electron in, we have to fill the 2s orbital next. And so for lithium, we see we have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. And if we move to beryllium, the 4th element in the periodic table, we'll have 4 electrons. 2 electrons in the 1s, 2 electrons in the 2s. You can see here each electron is unique to its orbital. That is, there's 1 upspin and 1 downspin per box. If we continue to fill these boxes with electrons, so moving from beryllium to boron, we can place our next electron in the 2p box. Now, it doesn't matter which p box I pick to put it in. They're all equal in energy. That is, all 2p orbitals have the same amount of energy. However, the 2s and the 2p are not identical in energy. So I can pick any one of these 3 p boxes to put in an electron, and I'm just going to put the next one in. So I've got the up arrow representing the spin of the electron, and we can continue on to carbon. Now with carbon we have a choice to make, and the choice is, do I put a down arrow in the box with the up arrow, or do I spread out and put another up arrow in the box next to it? Both are possible choices. However, there's only one correct way in which electrons fill, and that is they spread out. Why pair up 2 negatively charged particles in the same region of space unless you have to? So things spread out. And so all the boxes will take one up arrow before we have to start pairing up electrons in these boxes. So the diagram on the right is the correct view we should have for the electrons surrounding carbon. We move on to nitrogen. We complete this p orbital, so each p orbital has one box. And if we move on to oxygen, the next electron goes into one of those p orbitals with a downward spin. So when we fill up when we fill electrons into orbitals, we have this rule known as the Pauli exclusion principle that says no two electrons in the same atom can have the exact same energy. That is, you can't have two electrons with the same spin occupying the same spot. You can have an upspin and a downspin, but you can't have two upspins or two downspins in what's known as the ground state. That is when the electrons are all as close to the nucleus as they can be. Now, we're ultimately interested in writing electron configurations and being able to describe just how many electrons are in each orbital. And so here we've got an example of an electron configuration where we have the principal quantum number, that's the first thing, so the 4. We have the letter designating the type of orbital, in this case it's a p, and then a superscript describing how many electrons are in these orbitals. In this case, there's 5. When we fill electrons into orbitals, we must obey Hund's rule. And Hund's rule basically says for degenerate orbitals, the lowest energy is obtained when the number of electrons with the same spin is maximized. That is, electrons will spread out before they pair up with their opposite spin. So all the orbitals will take an upspin before they will take a downspin. You cannot have, for example, an up, down, and up in one particular set of orbitals. The electrons always follow suit. They always copy what was previously done, and then they will change only once all the orbitals have filled up with an identical type of electron. We describe this as maximizing spin. So if you look at nitrogen there, you can see in the 2p orbital, all 3 electrons in that 2p orbital have the same spin, they're going up. We wouldn't, for example, put an up, down, and up, because that violates Hund's rule. So when we set up the periodic table, we fill in the periodic table based on the electron configuration that a particular element has. So when we look at the periodic table, and we'll just take a look on the next page here, the periodic table is broken up into what's known as the S block, the P block, the D block, and the F block. So right here, columns 1 and 2, this is known as S block. Over here, with the exception of helium, this is known as P block. Down here in the middle is D block, and then these guys over here is known as F block. So the elements are arranged in terms of blocks. Now, when we describe the reactive properties of atoms in their respective columns, they have the same reactivity because basically they have the same outer electron. It is the outer electrons which are responsible for the patterns we see in chemical behavior. So you can see in the first column here, we have 1s1, we have 2s1, we have 3s1. They all have this outer S1 electron, which is the furthest electron away in their respective elements. And so because there's one electron in that outermost orbital for each and every atom in column 1, they all have similar properties of reactivity. So the periodic table, the reactivity of columns is responsible for the outermost electron and how it behaves. When we describe the outermost electrons, we are describing what's known as the valence electrons. Only the outermost electrons in any given element are responsible for reacting. all elements, in terms of their reactivity, are trying to become like noble gases. They want all their orbitals full with the electrons. So the s, the p, the d, the f, they're all seeking to get to the state where all their orbitals are completely full. And so when we talk about the formation of something like a sodium ion, which has an electron configuration here of, and we'll just write it out, there's sodium. We always start by looking at how many electrons we have. So sodium's got 11. And what we're going to do is we're going to start at the top and work our way over. So the first orbital we always fill is 1s. And the 1s orbital at most can hold 2 electrons. The next orbital is the 2s. And it can hold at most 2 electrons. So we've gone 1, 2, 3, 4. We still have another block of electrons to go through, and that's the p. And it's the 2p because we're on the second row. So we have 1, 2, 3, 4, 5, 6 to get to neon, so 2p6. 1, 2, 3, 4, 5, 6. And then we finally get to sodium, which ends with 3s and 1 electron in it. So one thing we know about column 1 elements is that they form cations with a +1 charge. So the sodium ion here loses 1 electron. Well, which electron does it lose? It loses the outermost electron. And so the sodium ion has a configuration of 1s2, 2s2, 2p6. It's lost that 3s1 electron. And so what we've got left behind are electrons from the previous row, which are all full. These are known as core electrons. So every time you complete a row, you will have completed the maximum number of electrons allowed in those orbitals, and you have essentially filled what's known as a core. So in the sodium atom, there are 10 core electrons and 1 valence electron. In magnesium, we have 10 core electrons, because that's the last row that was filled, and we have 2 valence electrons. Aluminum has 10 valence electrons, and we have 3 valence electrons. So we work our way over, and what we see is we get increasing number of valence electrons as we move from left to right. Okay. So there are a couple of instances that you should be aware of for filling purposes, and I just want to point them out here. That chromium and copper and silver have weird exceptions to their electron configurations. And those are the 3 that I want you guys to be aware of, in that orbitals like to be either empty, full, or half full. And when it comes time to d orbitals are allowed to cheat. So are f orbitals, but we're not going to focus on f orbitals. D orbitals, if they're 1 away from being half full or completely full, they will steal an electron from the s orbital and fill up the d orbital, or halfway fill up the d orbital, because 2 half full orbitals, or 1 half full and 1 completely full, is more stable than having a state that isn't half or completely full. So chromium has an electron configuration of 4s1, 3d5. Copper has a configuration of 4s1, 3d10. And so what we find is that these atoms are more stable than other elements in their same row. Now, if you look over here, we see this parentheses, or this bracket with argon in it. What does that mean? Well, that basically means when you write out the electron configuration, argon is all the core electrons, or perhaps better saying that all the electrons argon has is the same configuration. So when we put brackets argon, it's a shorthand notation of saying 1s2, 2s2, 2p6, 3s2, 3p6. This is known as noble gas configuration. Rather than continuing on and writing out every single orbital, we can save some time by putting a bracket and using the previous row's noble gas. So if I was doing barium's electron configuration, for example, I could use bracket xenon and then just write 6s2. So there are some weird anomalies. These are the three I want you to be aware of. And you should be able to write the electron configuration for any element in the periodic table going down to barium here. Okay. So with that, I will wrap it up.